Hello everybody and welcome to this video, kindly sponsored by Magellan TV. Now as you know, I don't take that many sponsors, and the ones I do I curate to make sure they are relevant to the interests of people who watch this channel. And in this case, amongst the several thousand documentaries that they have, there are quite a number that I think you'll find particularly interesting. Regular viewers will know I'm quite keen for the words of those who are actually there to be heard. And in that respect, there are documentaries covering everything from the end of the Second World War with the surrender on USS Missouri, through to the start of America's involvement with remembering Pearl Harbor, and all the way back to the Last Voices of WW1, voices that nowadays pretty much are all gone, but they've managed to record them so we can hear what it was like to actually be there. And as well as more recent 20th and 21st century history, they've also got ancient history, science and technology, a whole section dedicated to space, and sections for other interests as well, like nature documentaries. So there's something to be seen for all the family. And you'd be surprised how often one of those topics ties in to one of the others. So if you're interested in watching these or any of the other excellent documentaries available on the platform, please click on the link in the video description below or use the QR code appearing on screen now, and you'll get a 30-day free trial to experience the entirety of Magellan's catalogue. Thanks very much once more to Magellan, and now on with the rest of the show. The battleship's main armament is of course the big gun, but there's a surprising amount of complexity behind the construction of battleship guns, at least in the era of dreadnoughts. So let's take a brief, if somewhat deeper, look into it. Back way at the start of naval gunnery, guns were generally made of bronze. This was because iron guns, whilst cheaper, had a horrible tendency to randomly, but distressingly frequently, explode. Additionally, iron was of course subject to rusting quite quickly in the moist saltwater environment of the sea, which ships tended to be in, and that meant that the various components that made up an iron gun could become even less well fitted and even more dangerous as time went on. There was only a certain amount that cleaning and painting such weapons could do. Of course, early iron guns are where we get the term gun barrel, as the first such weapons were built using the same techniques as wooden barrels, namely a series of staves that made up a cylinder which was then bound with hoops, as can be seen in the cross-section of one of the guns that was recovered from the 16th century English warship Mary Rose. Bronze, on the other hand, could be relatively easily melted and then cast as one large item, which could then be cleaned up and bore evened out before it was accepted into service. These guns, when properly made, didn't tend to explode, and even a failure could often lead just to the gun bulging rather than shattering. Bronze was of course significantly more expensive, but a worn-out bronze gun, as repeated firings would eventually work harden it to the point that it might well actually crack, could just be melted down and recast. The advent of better casting techniques for iron during the 16th century would gradually allow for more reliable iron guns to be made, initially starting with small ones and gradually working up in size. Since these were much cheaper, generally speaking, they gradually overtook bronze cannon as the weapon of choice, especially as this also coincided with ships starting to carry more and more guns per ship, and the numbers of ships that the state kept in service was also generally growing, although whether one led to the other or vice versa, I leave to you to decide. Bronze would remain in use for very large guns, where iron casting took a little bit longer to catch up, and on prestige ships for a couple of centuries, but by the late 18th century, a long gun in bronze would be rare enough to be worthy of comment. For example, the HMS Victory that comes prior to the existing HMS Victory carried 42-pounder bronze long guns on her lowest gun deck, but of course the current HMS Victory only ever used iron guns for the majority of her service, including that lower gun deck where it was typically iron 32-pounders. And of course the much earlier Mary Rose, which we mentioned previously, carried a mixture of iron and bronze guns, with the iron guns themselves also being of a mixture of construction techniques. Iron, and later steel, were thus the materials which were used to make a ship's armament in the 19th century. But the basic principle of casting a large metal object, sometimes with a sacrificial insert to form a rough barrel or bore, and then boring that out and forging the resulting single piece of metal into a naval gun, remained pretty standard until the latter part of the 19th century. At this stage, guns had grown, well, quite large in some cases, but also around this time, rifled guns began to appear in major naval artillery, and a switch in construction methods can also therefore be observed. This switch results in guns moving over from a single-piece monolithic construction technique to what was referred to as a built-up gun, at least usually referred to as such, a term which later takes on a slightly more specific meaning, as we will see, but essentially it means a gun that has been built from several components rather than just being a single monolithic lump of metal. This change occurred for a number of reasons. Firstly, and to be honest, most importantly, was an issue that would limit the overall size of naval guns consistently going forwards, which was how large a lump of steel could you cast with a reasonable degree of quality control. With the advent of rifling and large guns, a gun would have to be cast as a solid mass and then bored out entirely from scratch. The chances of warping, differential cooling, and such like were far too great for some kind of sacrificial void space insert to be used as had been done on smoothbore guns from earlier periods. And this meant that if you wanted a gun that weighed, for example, 20 tons, you needed to be able to cast a single lump of steel that might weigh 25 to 30 tons, and then have the lathes, hammers, and presses to bore and forge this mass into a weapon. Now, even assuming you could technically do this, the sheer number of guns that might be expected to be mounted on a typical warship of the 1870s or 1880s, and the number of ships that needed these guns, meant that, realistically, it didn't actually matter if you had one or two factories that could do this at a very slow rate, because you needed to be able to make dozens of such weapons. And that lowered the practical limit of what your gun foundries could typically make somewhat below the industrial threshold of your economy, with the exceptions for specific prestige weapons that you might only install on one ship or in one location. Separately, of course, the kind of metal that you needed to make durable rifling, which tended to be exceptionally hard steel, was entirely unsuitable for making a gun out of as a whole, at least at this scale. A hard and relatively brittle material, which is good at keeping its rifling, would crack or shatter under the significant stress of a battleship-grade cannon firing and all that propellant igniting, and this would occur with little to no warning, as did actually happen several times in the middle and latter part of the 1800s. Instead, a bit like battleship armour, you would need a combination of harder steel, internally, if you like, the business end of the gun, but backed up by softer, more ductile material which could absorb and withstand the stresses imposed by firing the gun. These and other issues could be solved by making a relatively thin barrel, or liner, as it was often called, and then encasing it in multiple cylinders. Often the terms such as hoops or jackets would be used, and these could be made of other steel. More or thicker hoops could be applied at the breech end, since that's obviously where the pressure was the highest, and this applied pretty much regardless of whether you were making a muzzle or breech-loading rifled gun. This, in turn, now meant that your ability to make a really big gun was still constrained by your maximum workable ingot size, was significantly increased overall, since any one ingot only needed to be made into part of a gun, instead of made into the entire thing. So, for instance, if you could only make a 40-ton ingot, but you had a gun design that was made up of 5 separate elements, the largest of which weighed 20 tons, or perhaps all of which weighed 20 tons, then as long as the removal of material from a 40-ton ingot left you with enough for 20 tons to be left over for the component, you could assemble a 100-ton gun out of 5 20-ton components, despite not actually being able to cast a single lump of metal, even half the final weight of the weapon. This method of construction would be utilised for the majority of battleship guns throughout the pre-dreadnought and dreadnought era. So let's go into a bit more detail about the process of the construction from start through to finish. It would all start with the smelting of metal. Now, typically, this would be made up of some new pig iron, which would be smelted from iron ore in a blast furnace, which would then be mixed together with other pre-existing steel, usually scrap, which was melted in an open hearth furnace. From this somewhat bubbling and very brightly glowing liquid, the various impurities could be skimmed off, and as time went on and guns developed along with metallurgy, various additives could also be included at this stage, which would change the overall composition of the steel in question, whether that be slightly altering its carbon content, or adding trace metals for things like better corrosion resistance, better tensile strength, or other features you might want, depending on which part of the gun this particular batch of steel was due to make. The molten steel would then be poured into giant moulds, and depending on the time and the manufacturer, these might be cylindrical or faceted blocks. Once this casting had cooled and been extracted, it would then be heated again until it was glowing, and transferred over to a large press. Early on, you could use steam hammers, although later on either presses or hammers could be hydraulically powered, and presses in general came to be preferred. Whatever you were using, these would then compress and elongate the ingot in much the same way as a blacksmith would forge a billet of steel out into a sword, only on something of a macro scale. The ingot would be rotated after each press or blow in order to even out the resulting billet, which would now look roughly like a basic gun barrel, at least as long as you looked at it from the side, as if you looked at it from the front, the lack of anywhere to put the shell would be fairly obvious. As with smaller scale forging, the mass would sometimes need to be reheated, but the sheer thermal mass of so much metal meant that generally it could retain a working heat much, much longer than something you'd typically make using a hammer and anvil. Now, at this stage, having been compressed and shifted around in all sorts of directions, the billet would be under significant internal stress, and so it would be annealed to the degree that was applicable for its intended use, whichever part of the gun it was supposed to make. Annealing consisting of reheating it to a given temperature, but one lower than either molten or exceptionally brightly glowing, and then slowly cooling it down. This cycle could be repeated several times at various temperatures and at various lengths, again depending on the final qualities of the metal you were looking for. There would be a further annealing process further down the line, but this was the first one, so this is where you get the explanation of how that's done. Next was the boring process, and that doesn't mean it was uninteresting, it was literally boring with a giant lathe. This turned the cylindrical lump into a tube, and if the tube was going to be the liner of the gun, then it would also need to be rifled. Now, cutting the rifling is a process that requires extreme precision and extreme delicacy for the time period of pre-dreadnought and dreadnought guns, but it also requires immense force, since the metal that's being cut will itself be quite hard. With something this size, you just can't start cutting whilst the barrel is still glowing and relatively soft, because you will almost certainly end up with slight movements internally, which would ruin it all. Of all the processes that go into making a battleship gun, this process is the single most fraught. Almost every other step can be redone, or a failed element replaced, unless of course you overboard the billet in the first place. But the slightest misalignment or slightest step in the rifling would mean that the whole process up to this stage has been wasted and the liner just has to be scrapped, with the entire process starting over again. The outer face of the billet would also be milled down, regardless of whether it was a liner or some other part of the gun, as the hammer or the press would have brought the overall size of the ingot down close to, but not exactly at, the final desired outside diameter. Only the mills and the lathes offer the fine control on the dimensions that's needed at this stage. Assuming that a working liner has been produced, the gun can then begin assembly. For a built-up gun, this would consist of another cylinder that ran the whole length of the gun, which was milled and bored to fit the liner, which would include any expansion at the breech end. This would then be made to an inner diameter, which was ever so slightly less than the outer diameter of the liner. So close that you might well be forgiven for mistaking the two dimensions for being exactly the same, but nonetheless, this cylinder, which was called the tube, would then be heated, taking advantage of the fact that metal expands when it is heated, thus making the internal diameter slightly larger. It would then be lowered over the liner, and the two components could be cooled down. By the dreadnought period, this was also done under pressure to ensure that the contracting steel cooled and settled evenly. Thus, the tube and the liner were held together by both immense pressure and immense friction, which would prevent them from coming apart. This also had the advantage of exerting constant inward force on the liner, although not above its elastic limit, so that when a shell was fired and the pressure inside the gun built up and tried to force its way out, it first had to overcome this compressive force before it could begin to exert stress on the tensile resistance of the tube and any subsequent components. The principle of deliberately putting tension into a system, opposed to the expected loads, is one that's actually quite common in engineering in a number of fields, albeit that when it fails, the released tension can lead to some quite spectacular results. Now, terminology can vary slightly by country and time period, but from most English language sources, you would have a jacket installed over the tube, which is installed over the liner. The jacket would usually also run the full length of the gun, but be made up of two or more segments, as opposed to the tube, which was one segment. And outside of this would come various hoops, which were also cylinders, just not full length, and these would gradually decrease in length as you got more and more of them further and further out in diameter, which would result in a much thicker breech end compared to the muzzle. Depending on exactly how thick and exactly what profile shape each of these segments was made to, you might see a series of very obvious steps in thickness. This is most easily seen in late ironclad and early pre-dreadnought era guns, or in later guns with somewhat more complex layering and a highly shaped outer hoop, you might only see one or two slight steps along the entire length. Stop rings, also sometimes called locking rings, could also be added in at various points, again depending on the gun design in question, as an extra layer of security against the various hoops and jackets, etc., riding up and down each other when the gun was fired, and the whole thing was subject to varying levels of tension as the shell progressed down the barrel. Now, if you were making such a built-up gun, then all of these outer layers beyond the liner would need to be assembled first, and then the whole collection from the outermost hoop down to the tube would have to be heated up again as one and lowered down onto the liner. This is what allowed guns to be reconditioned. The tube, the jackets, the hoops, etc. had service lives that really could be measured in the thousands or tens of thousands of rounds, since apart from providing structural support to stop the whole thing bending, their main role was just to resist the pressure of propellant ignition that was being transferred through the liner without undergoing plastic deformation. So, for those of you who may not know, elastic deformation is when material distorts, but is able to return back to its original state, much like an elastic band. Plastic deformation is where something distorts and then either remains at that level of distortion or may return slightly, but does not return to its original form. So, for example, if you watch high-speed footage of people engaging in historical European martial arts or medieval reenactment, you'll see swords perhaps hit each other, and you'll see the blade bend, but by the time they've finished their movement, the blade has returned to being straight. This is elastic deformation. Very occasionally, you might see someone hit somebody or another blade or something like that, quite often with something like a small sword, and when the movement is finished, the blade is now visibly bent, even when stationary, and this is plastic deformation. The problems with plastic deformation when it comes to guns is not only is the gun potentially now not in the alignment you actually wanted it to be, but also plastic deformation involves some kind of destructive process having gone on at the microscopic level, which could foresage some rather dramatic failures rather quickly. The liner, by contrast, would be worn out by both the temperature of the burning propellant and by the passage of the shell along the rifling rather quickly, as it would degrade very slightly with each firing. Thus, the liner might only have a life cycle of a few hundred rounds, possibly even less. However, by reversing the process used to assemble the gun, so heating it up again to make it expand again, you could loosen the fit between the liner and the rest of the gun enough to withdraw the expired liner and then insert a brand new one, which meant to keep using the gun, you only had to manufacture multiple liners instead of entire guns, at least in theory. The different alloy material ratios in the liner compared to the rest of the gun would aid in this, as the expansion of it and the tube and all the other surrounding elements surrounding it occurred at slightly different rates, thus exacerbating the gap. However, at times, some quirk of usage or just the gun design would mean that the liner could not be extracted. In that case, the liner, if you wanted to continue using the gun, would have to be bored out entirely, a much longer and much more costly process that could damage the rest of the gun enough to make it unusable if you weren't very careful. Typically, although, as mentioned, you could just keep reusing the same gun, navies would order more guns than were needed for the ships that they built. For example, the two Nelson-class battleships of the 1920s needed a total of 18 of their big 16-inch guns to arm both of them at the same time, but a total of 29 were made. This allowed for catastrophic damage in battle or some kind of fault to render a couple of guns irrevocably useless, whilst still maintaining a full battleship's worth of stock ashore. Then, if a ship came in with every single one of its main guns worn out, which was unlikely, but theoretically possible, you've got to bear in mind that not all guns and not all turrets fired at the same time in typical usage, and so one or more guns might wear out considerably faster than others. But anyway, even if every single gun on the ship was worn out, the ship could be relatively quickly re-equipped with a whole new set of working guns taken from the stock ashore and sent back out. The worn-out guns that had just been removed could then be taken off to the gun factory and undergo the process of having their liners replaced, and thus they would now become the ashore stock for when the next ship arrived. More typically, only a few guns, or perhaps even one, would need replacing, and that could mean that different guns could end up serving on different ships in very weird orders. For example, if you look at the two 15-inch guns outside the Imperial War Museum, each of them has a rather interesting service history, being mounted in various ships, having been taken off of one for reconditioning and then reinstalled on another when it came in. Speaking of, on a much larger scale, there were a total of 184 mainline production 15-inch 42 guns manufactured, plus a couple of prototypes, despite the sum total needs of all 5 Queen Elizabeths with 8 guns, all 5 Revenge class with 8 guns, Hood with 8 guns, the 2 Renowns, each of which had 6 guns, plus Glorious and Courageous, each of which used 4 guns, and 4 Monitors, each of which used 2 guns, meant that the single greatest demand level for them, reflected by that list of ships, added up to only 116 guns. And yes, I know there were a few additional 15-inch monitors manufactured later on, but by that point Glorious and Courageous had been converted to carriers. But there was an alternative to this. Starting in the 1880s, there were also what came to be called wire-wound guns. Now, the actual technique had been invented a little bit earlier, but it was in this period that the technique was applied to battleship-grade weapons really in earnest. This method started being used because guns were growing very rapidly in size, but the technology to work with the very large castings involved, as we've mentioned earlier, was limited. So, as an alternative, once the lining and the tube had been put together, what you could do is take a very, very long spool of steel wire, usually using wire with a squared profile as opposed to round wire, which we might be more familiar with. And please note, this doesn't necessarily mean that the wire has a perfectly square cross-section. It's just that the wire has 4 corners, each of which are 90 degrees. So it could be square, it could be rectangular. And this meant that the wire could be laid next to itself in a coil without leaving significant air gaps. Now, in any case, this wire would then be wound under colossal pressure. We're talking about 6-figure PSI along either part or the whole length of the gun, again, depending on the technique, nation, and time period. And varying numbers of layers would be used, usually with more layers towards the breech end, after which solid hoops would be applied as with a built-up gun, and the whole process finished as previously described. So essentially, the wire winding would take the place of some or all of the jacket and some or all of the hoops, but not all of them. The tension applied to the wire and the actual physical size of the wire in the various layers could also be quite variable. Now, there are advantages and disadvantages to the built-up and wire-wind methods. Unfortunately, most of the literature of the time, and to be entirely fair, much, although not all, of the writing subsequent, tends to play up the advantages of one method and the disadvantages of the other, almost proportionally to the nationality of the writer relative to the nationality of the nations who used one or the other method primarily in a good chunk of their history, since wire-wound guns found most traction in the UK, Japan, and up to World War I, Italy, whilst Germany, the USA, and various others tended to mostly stick to the built-up method all the way through. And this bias makes analysis of the benefits of each as much a matter of national posturing as anything else quite a lot of the time. Other nations, of course, imported overseas guns, which can make working out trends in those nations' navies very difficult because, their ashore manufacturers might prefer one technique, but they might be importing guns from another country that manufactures them using the other. And this isn't helped by the fact that some considerations on both sides of the argument materially changed as metallurgy and machinery advanced over time. And so some assertions made for or against a particular method are true in some decades, but untrue in others. Briefly, the primary advantages of a wire-wound gun are that the quality control of the binding material, the wire, is much easier to both assure in the first place and to monitor as it's being applied, because the wire itself is relatively thin compared to a big jacket or hoop, and the technology to make good quality steel in relatively thin amounts is much more developed than the considerably larger jackets or hoops, which, as we've said before, were usually on the cutting edge of technology of the period. This is actually very well exemplified by the Japanese attempts to create a monster gun in the 1920s, the predecessor to the Yamato's guns. This almost failed in construction partway through when entire hoops had to be abandoned at the very last minute when previously undetected flaws became evident in the form of cracks, as they were called, onto the rest of the gun assembly. Whereas it was possible, in that case as a stopgap, to replace these units with wire winding. The overall failure of that particular gun in final testing was more to do with just the sheer size of the weapon versus the industrial capabilities of Japan at the time, rather than the benefits or drawbacks of any particular construction method, because that particular gun was a hybrid of both. Additionally, for the first 3 to 4 decades, wire-wound guns could actually be made lighter for the same strength or stronger for the same weight compared to built-up guns, thanks to the wire being able to be applied under extreme but controlled tension, and due to its somewhat more elastic nature thanks to the way it dealt with expansion forces, which meant that a lesser amount of tensioned wire could reliably contain the same amount of force as a larger cast and forged piece of steel. This advantage, however, disappeared somewhere in the 1910s as more advanced alloys increased the tensile strength and reliability of the steel hoops and jackets. It was also generally held that catastrophic failure was safer with wire-wound guns, since material failure in such weapons tended to lead to a rather dramatic unspooling of the wire, but this, again, generally tended to leave a barrel dropped on the deck and the world's biggest and messiest slinky, since somewhere between 100 and 200 miles of wire could be used in a typical 45 caliber length dreadnought era gun. Conversely, a built-up gun that suffered catastrophic material failure would tend to fragment in many directions all at once like a giant grenade. Not to say that wire-wound guns couldn't do this, but they tended to do so somewhat less often. On the flip side, of course, wire-wound guns had less longitudinal strength, that's from breech to muzzle, because, of course, the wire that was wrapped around it doesn't offer much help in this direction, hence the need for the solid hoops and/or a jacket outside of the wire. Now, this could result in drooping under extended firing as the gun heated up, or whipping when shot as the vibrations and forces travelled up the gun, and this could cause inaccuracy, albeit that this in part depended on the skill of the gunmaker in supplying the right amount of tension to each layer of wire, and what other methods might have been used to mitigate these effects, such as flaring the muzzle slightly. It should, of course, be noted that HMS Warspite holds the joint longest shot for hitting a moving target from a battleship, and her guns were wire-wound, and the 15-inch 42 was generally known to be a very accurate weapon. Also, wire winding requires a rather large investment in specialist machinery to both make the wire and to conduct the winding, whereas the same equipment of lathes, presses or hammers in the earlier periods, etc., that makes the liner and the tube could also be used to make the jacket and the hoops of a built-up gun. It's just slightly different sizes. There's also the matter of replacing the liner, but in this case, literature on both sides very loudly and confidently asserts that their method is superior and the other significantly inferior for the removal and replacement of a gun's liner. So I'll leave that one for you to make your own decision on. Once the gun itself is now mostly assembled, the rather important breech block has to be added, with provision for its fitting having been made during the manufacturing process. By the dreadnought period, this took one of two forms. The more common was the interrupted screw breech. In this, a vaguely dome-shaped breech seal was presented to the back end of the gun's chamber by being swung in on a hinge. A series of stepped partial screw threads worked into the rest of the breech block would then allow the whole thing to then be turned, engaging with the receiving threads in the barrel section of the breech, and this short turn finalised an already reasonable seal and ensured by the sheer number of threads that the block was strong enough to maintain the seal against the pressure of the propellant ignition. This, in turn, allowed shells to be fired using only bagged charges, which ideally completely consume themselves in the process, facilitating a slightly faster reloading system and a smaller amount of equipment in the turret when compared to the alternative. Said alternative was the sliding breech block system. This was technically speaking a simpler system in which a large lump of steel would slide down across the breech to close it. Whilst simple in principle, it did have a number of slight disadvantages. Firstly, the breech block had to be contained itself, as opposed to fitting in with the body of the gun to stop it flying backwards when the gun was fired, and this slightly increased the weight of the gun. And to make it possible to close the breech without absolutely massive amounts of friction and thus permanent jamming, the seal could not be absolutely perfectly gas tight. Thus, using bagged charges would result in pressure leakage around the breech, which could range from annoyingly inconvenient to completely deadly, and would always compromise the accuracy of the gun, as a random amount of pressure would be lost in this way, which of course lessened that which could be sent into the shell down range and potentially also meant the application of pressure was uneven. The solution to this was for the last charge segment to be in a brass casing, much like a giant bullet. The soft brass would then form the remaining element of the seal when it was blown back and expanded by the force of the propellant ignition, or for that matter, pinned in place by the closing of the breech block. Whilst this slightly reduced the risk of magazine fires, as a portion of your charges were now contained in hard metal, it also increased the weight of the ammunition, and it meant that you had to have a process to extract, deal with, and hopefully eject the extremely hot brass casings every time you fired the gun. There was also the issue of where the sliding breech block went. On a battleship scale, a vertically mounted unit could impact on your ability to elevate or depress your guns, unless you made the turret taller than was strictly otherwise necessary, or the gun pit deeper, both of which would increase weight, and in the former case, also increase the target area of the turret for enemy shells. Or you could mount them sideways, which obviated those problems, but it meant you needed more space on the side of your gun that an interrupted screw breech, whose horizontal profile was usually mostly within the scope of the width of the gun itself, did not require. As a result, sliding breech blocks tended to be used on smaller guns, unless of course you happen to be Krupp, whilst at certain calibers, most large naval guns would switch over to interrupted screw breeches. The exception to this was when it came, towards the end of the Dreadnought and Battleship period, to auto-loading guns. In those cases, sliding breech blocks and brass case charges lent themselves far more easily to automation using 1940s era technology, and so, for example, the 8-inch guns on a New Orleans or Baltimore class heavy cruiser used interrupted screw breeches, but the auto-loading 8-inch guns on the Des Moines class used sliding breeches, although the guns otherwise shared quite a lot of common features. So that wraps up a brief overview of how battleship guns were made. If at some point you want me to go into the finer details of the mechanics of hardening steel and heat treating it, annealing, quenching, and all that sort of lovely stuff, which also is of course relevant to battleship armour design, do let me know in the comments below, and I will perhaps accelerate when that is discussed later on in the channel. Anyway, thanks for listening.
That's it for this video. Thanks for watching. If you have a comment or suggestion for a ship to review, let us know in the comments below. Don't forget to comment on the pinned post for dry dock questions.